Okay, so any questions? Well, up to now, what we had done was we were discussing about the probabilistic statistical concepts. We defined how to relate these statistical concepts to entropy, and we had basically studied the ideal gas in this simple system with this simple approach, let's say, and then we saw that everything is kind of consistent. Now let's try to be a bit more formal on what we are doing, what we are actually doing. So today we will be starting to deal with ensembles. Now, what is an ensemble? Or in fact, if you think of what is a measurement. So let's say that you are measuring the pressure. You cannot really measure the pressure at a given instant. And if we could actually measure the pressure of, let's say, the ideal gas, very precisely, this is what we would have observed. So loss of fluctuation. So when we actually measure, when we measure the pressure, what we are actually measuring is some kind of a time average. So when we talk about the measured value of some quantity, this is the average over time of that quantity from, let's say, some t0 up to t0 plus t. And this t is something large enough over a large time interval. Now, if you imagine what the system does within this time interval, well, these measured quantities, they give us, like the pressure, the energy, etc., they give us the macro state of the system. And we know that in equilibrium, at least the way we define equilibrium, is that in equilibrium, these parameters defining the macro state do not change in time. But nevertheless, the microstate of the system is constantly changing. You see, even if you look, for example, classically, the microstate is defined by the position and momentum of all the particles making my system. Since they are always moving, their position is changing, and they are colliding with each other, and the walls, their momentum are constantly changing. So at the end of the day, with time, the microstate of my system is constantly changing. So although the macrostate is constant, the microstate is a constantly changing function of time. And when we take this average over time, we are in fact actually taking an average of various microstates of the system. Because during this time interval, the system is changing and visiting many microstates. So this time average is actually an average over different microstates of my system. Because this observed quantity changes over time, mainly because the microstate of my system is changing over time. So the time dependence is actually the microstate dependence of this observable. So this time average would be the average over the microstates that my system is visiting in a given time interval. But rather than this, we can have a different approach. Let's say we have a given macrostate of my system, and we can imagine different microstates. Well, before starting that, let us describe what we mean by phase space. Now, the microstate of my system is defined by the positions of each one of the particles and the momentum of each one of these particles. So if I have n particles, then I have 3n positions and 3n momenta. In total, this is just nothing but a 6n dimensional space. And my microstate of the microstate of my system is just a point in this 6n dimensional space. Let's say these are the momenta coordinates, these are the position coordinates. So this is just a point in this phase space. And in time, this point is just moving around in phase space. Now, a simple example would be the harmonic oscillator. a one-dimensional harmonic oscillator, in which we know that the microstate is determined by the fixed energy, if it's an isolated system, let's say. Then the Hamiltonian is p squared over 2m plus 1 over 2m omega squared x squared. This is E. This is a condition imposed by my macrostate. So this is basically a two-dimensional phase space. And this my macrostate basically selects a hypersurface in this two-dimensional phase space. In this case, this is just an ellipse. This is the available phase space to my harmonic oscillator of a given energy E. Now, just like in this one, in general we have this phase 6n dimensional phase space for a system, a three-dimensional system, and any constraints I have, for example, if the system is isolated and the energy is fixed, then that chooses a hypersurface in this phase space. And the point corresponding to my system in this phase space is basically moving on this hypersurface, or some kind of a volume, let's say. If you just say that the energy is finite, rather than giving a fixed energy, that would just define some volume in this phase space.
Birkaç dakika içinde geliyor hocam.
Now, what we will do next is, okay, we said that on one hand, this my system is moving in this phase space, and what I measure is actually a time average of my system, and which is basically an average over the microstates that my system visits during this time. Another thing we can do is, let's just look at all these microstates at a given time. Let's just imagine I have many copies of my system. And in general, what will happen is each one of these copies will be in a different microstate. Now, we said that the measured value is a time average. And if this time is somewhat long enough, my system will be visiting a representative sample of all the microstates. Available to my system, consistent with the constraints. So if I know all the microstates corresponding to my system, or if I have many copies of my system, each one in a different microstate, then taking an average over all these copies would be an average over the microstates of my system, which is an average over time. So instead of taking a time average, I can take an average over all these copies of my system at a given time. So these copies are what we call the ensemble. So instead of just taking one system, let's look at this harmonic oscillator example. Instead of taking this one system and following its trajectory in phase space, well, I can take many copies of the system, and unless I arrange some special constraint on my copies, they will be distributed over the trajectory. Now, one question is, how will they be distributed? Will they be distributed uniformly, non-uniformly? Will they accumulate at some point? And there will be, the density will be less. Another point, that's another issue that we will discuss. But nevertheless, rather than just taking one system and following its trajectory over a time, I can just take multiple copies of the same system. And unless I made special arrangements, unless I impose special constraints, all these systems will be a representative sampling of all the available microstates. And taking an average over this ensemble would just be equal to the average over the time. So this, let's maybe note it by this one. Ensemble average will be just sum of the values of Fi times the probability of that value in the ensemble. And at the same time, if my system is in equilibrium, this will be nothing but the time average, which we said that this is nothing but the measured value. So that is what we will be measuring. Of course, here we are making some assumptions, such that we are assuming that at least given enough time, the system will visit all the neighborhoods of all the available phase space. That's an assumption. And this is what is called the ergodic hypothesis. It doesn't necessarily hold all the time. One example, for example, where it will not hold is if you, let's say, if you have such a potential and your system has energy this much, and you start your system, let's say, over here. For such a system, at least classically, well, your system will be confined over here. But if you just pick up a random ensemble, the members will be either on the right well or on the left well. So for example, in this system, the ergodic hypothesis does not hold because there are some additional constraints on my system, which we have to take into account. But of course, the system will still be visiting all the microstates consistent with my constraints, meaning that I am constraining my system to this half. So if I also take that constraint into account, the ergodic hypothesis will still hold, because it will visit all the microstates. Now, so just imagine this now. We have this 6n-dimensional phase space. On this 6n-dimensional phase space, and I have my physical system, and I have many copies of them. Each one of these physical systems basically correspond to one point in my phase space, just like over here in the harmonic oscillator example. Rather than looking at one harmonic oscillator, I just made many copies of the harmonic oscillator. And all of these harmonic oscillators will correspond to some point in my phase space. And of course, ideally, we will be taking almost infinitely many copies. And if we take infinitely many copies, we can ask the question, we can define the density of these points in phase space. So rho PQ is the density of points in phase space corresponding to the ensemble. So basically, if you imagine some volume, let's say dp dq, the number of members of my ensemble within this volume dp dq would be just rho pq So this product would be just rho is the density times the volume. It's just the total number of the members of my ensemble within that volume. Well, as I said, ideally you would be considering, let's say, infinitely many of them. In that case, this number would also be infinite, but that's just a normalization issue. So you can just normalize. So if rho is normalized to 1, then we can identify this rho as the probability density. This is the probability that are randomly chosen member of the ensemble is in the volume dpdq. It's just a matter of normalization. Now, although I'm not writing it explicitly, this function can depend on time also. There is nothing that would prevent the time dependence. For example, you can have a system which is under the influence of an external time-dependent potential. Then this rho will be time-dependent, explicitly time-dependent. It's already, okay, it will be explicitly time-dependent. Now, of course, we will be dealing with stationary systems. So in our case, the explicit dependence will be 0. But, I mean, we will impose that constraint later on. Now, let's see how this rho changes with position and time. You see, this is the number of the member, rho, either the probability or the number of copies of my physical system. Well, the total probability, if you normalize it to 1, it should be constant. Or similarly, if you normalize it to the total number of the copies of your ensemble, well, the copies is fixed. I mean, with time or as the system evolves, you are not creating new copies. So basically, there is a conservation law. If you just consider some volume, integrate this over, let's say, the volume omega. So this is either the total probability inside the volume, or you can say that it's the number of copies inside your volume. And look at how it changes with time. Well, since this should be conserved, well, let me also write it in this form. If this number is changing within a given volume, well, that basically means that it is flowing out through the boundary of your volume. So there should be some flux over the boundary of our volume in phase space, which I can also write in this form. Which I can convert to a volume integral. And well, just combining these, it just tells me that this line is equal to this line, whatever our volume is, only if d rho by dt plus rho divergence of this quantity is equal to 0. Now let us make some definitions. The v over here is not the velocity of the particles. It is the velocity of the point corresponding to my system in phase space. So this is a 6n-dimensional velocity. So here the velocity is actually the momentum, time derivative of the momentum and the coordinates. This is the velocity in phase space. And the divergence is similarly derivatives with respect to the momenta and the derivatives with respect to the coordinates. This is the divergence again in 6n dimensional phase space. Now let us write this explicitly. So this is equal to d rho by dt. Let's try to see some simplifications. D over d pi. Rho vi is pi dot. Plus d over d qi. Rho qi dot. This should be equal to 0. This is d rho by dt plus d rho by dpi, pi dot, plus d rho by dqi, qi dot, plus rho dpi dot over pi plus the qi dot with respect to qi. This should be equal to 0. Now, first let's look at this one. But you see, this derivative is nothing but the total derivative of rho pi t. qi is a function of t and possibly explicit time dependence. So that 3 terms is nothing but the time dependence, time derivative of rho in what's called a comoving frame. So this point, pi qi, let's say, is moving, and you are moving with the point and looking at how rho changes at the position of that point. So this tells me that, okay, the third 3 terms is this one. Now let's look at the other 2 terms. You see, at the end of the day, although we are doing statistics, all of these particles are subject to, if it's a classical, in this one we are looking at a classical system, so classical dynamics. So they are subject to Newton's laws, or if you want, Hamilton's equations. And from analytical mechanics, you might remember that the momentum derivative is nothing but minus dh by dqi, and the coordinate derivative, the time dependence of the coordinate, is just dh by dpi. So because you see, this point is moving, this pi qi is moving, and its motion should be governed by the physical laws. So the motion of the positions and the change in the momentum of the particles making my system is subject to Newton's laws. So if I'm following a given point as it moves in phase space, that motion is actually governed by the classical dynamics, by these laws, whatever the Hamiltonian of my system is. Now in particular, let's say if you take the derivative of pi dot with respect to pi, this is nothing but the second derivative of the Hamiltonian with respect to first qi and then pi. But second derivatives I can always exchange. First I take the derivative with respect to pi and then qi. But if I first take the derivative with respect to pi, the second equation, it tells me that it is nothing but qi dot. So derivative of pi dot with respect to pi is equal to minus derivative of qi dot with respect to qi. So basically that tells me that the second term is equal to 0 because my system is subject to classical dynamics. So at the end of the day, what we obtain is d rho by dt, which is explicit dependence plus derivative of rho with respect to pi dot this is equal to 0. Well, let's just play with it a bit more. Well, pi dot, as we had just written before, is derivative of the Hamiltonian with respect to qi minus plus qi dot is derivative of Hamiltonian with respect to pi. But this is just the rho by dt plus the Poisson bracket of rho and h. This should be 0. Yeah, this is again just things that you should have seen in analytical mechanics.
By the way, why did you say d rho or dt is 0 in the beginning of?
No, okay. In this derivation, I didn't use it. So this is just a result of, let's say, the definition of rho and Newtonian dynamics. This is what's called the Liouville's theorem. So this basically tells me that this, in a sense, this a fluid, let's say, is flowing in phase space. This is incompressible. So if you are moving with the fluid, the density doesn't change. If you just imagine some very small volume element and just follow that volume element, its density is just fixed. Now let's go back to what I said before. Assume we have a stationary system. The system is not changing explicitly with time. Then d rho by dt is equal to 0. And what Liouville's theorem tells me that rho, the Poisson bracket of rho and h is equal to 0. For systems in equilibrium, of stationary systems, in fact. So this basically imposes a strong constraint on the possible values of rho, possible forms of rho. So this tells me that rho is a conserved quantity. Now we can put one more constraint on rho. It's not just an arbitrary conserved quantity. Let's just imagine, now to see where this constraint comes from, let's just imagine our system. And let's just assume that we divide it into two. And for each part of my system, I can define their own phase space, and so their own coordinates. Let's say this is Q1i, P1i. This is the point in phase space. This is Q2. Well, let me drop the P2. Let me drop the superscript I. So this QP just represents all the coordinates. And then I can also define the phase space of the whole system. And the phase space in the phase space of the whole system, I can talk about let's say, the probability density that my system will have my whole system will have the coordinates Q1, P1, Q2, P2. this probability density will be nothing but the product of the probabilities for the first system, rho 2, let me say this is the first and the second system, Q2, P2. Now the probabilities, if you have two separate events, the probabilities are just multiplied for the combined event. Now, there are several approximations we are actually making here. One thing is we are ignoring any effect of the interface between these two systems. But at the end of the day, that's what we call a surface effect. That any modification to this relation due to the surface separating these two subsystems, let's say, will be proportional to its surface. Whereas the other things that influence rho, let's say, they will be proportional to the volume. And if we have macroscopic systems, or what we call the thermodynamic limit, in which our systems are infinitely large, the surface is negligible. So in that approximation, this will hold. Well, what this tells me that logarithm of, if we look at logarithm of rho 1, 2, the density of the combined system will be the logarithm of rho 1 plus the logarithm of rho 2, the sum of the densities making parts of my system. So what do we know about rho now, or in particular logarithm of rho? Since rho commute, the Poisson bracket of rho with Hamiltonian is 0, the Poisson bracket of logarithm of rho with Hamiltonian will also be 0. But if rho is conserved, the logarithm of rho is also conserved. And the logarithm of rho of the combined system is the sum of the logarithms of parts of my system. So which tells me that logarithm of rho is not just an arbitrary conserved quantity, but it's an additive conserved quantity. So that quantity is just the sum of the corresponding quantities for the part of my system. But you see, there are not infinitely many conserved additive quantities corresponding to a given system. The conserved quantities, additive conserved quantities corresponding to a system are, what are the additive conserved quantities of a classical system?
Like mass.
Mass is correct. Well, it's just, let's say, some constants like mass. What else? Energy. Beta is just some constant. And linear momentum. And angular momentum. So this is the most general form of the logarithm of rho. But if I'm studying a macroscopic system, I can always go to a reference frame in which its total momentum is 0, and its angular momentum is 0. So I can just choose a rotating frame to make m equal to 0. If I am studying, I don't know, this eraser as it is rotating, I can just rotate with it, and in that reference frame it's not rotating. I can keep moving with it. In that reference frame, the p will be just 0. So without loss of generality, just by choosing my reference frame, I can always make sure that logarithm of rho is some constant, like the number of particles, minus beta e, or rho.
Why wouldn't beta go to beta prime in this transformation?
Fine, but it will have this form. You see, for the time being, I'm not really identifying what beta is. Or what C is, I don't know. I will identify it later on. But rho, the general form of this rho in phase space for a system in equilibrium, for a system in stationary state, should have this form. Let me just make this or e to the power c minus beta. Let me write it in this form. This is the most general form. I might have a system for which energy is also conserved. This number is conserved, energy is conserved. So C is a constant, E is a constant for my system. So rho is a constant. So if the total volume of my phase space that is available to my system is, let's say, omega, that rho is just, assuming it's just probability density, it's just 1 over omega. Constant. That is called the microcanonical ensemble. Or it might be that rho is, let me just change the constant to this one. If rho is, energy is not fixed, then my system can have different kind of energies. So this is called the canonical ensemble. Well, we will study each one of these separately later on. Now let's do some examples of microcanonical ensemble. Now, there's still one question that we need to address though. You see, before, until last week, we were looking at this omega. Number of microstates available to the system. Now in this microcanonical ensemble, we have rho, which we defined as 1 over omega. So we have rho, or if you like, we have omega. How are they related? Now, you see this omega is the total volume available to my system in phase space. So one guess would be, okay, if the volume available to my state is larger than the number of microstates corresponding to my that my system can have should also be larger. So I mean, it's kind of natural to expect that omega should be proportional to capital Omega, the number of states. And of course, if we convert this to an equality, we should write the number of microstates corresponding to my system should be the volume that is accessible by my system divided by some unit volume that each microstate occupies in phase space. Now then the question is, what is omega 0? Both classically and quantum mechanically. You see, classically, every point in phase space should correspond to a different microstate. but you have infinitely many points. So the number of microstates should be somehow infinite. And hence omega 0 should be 0, the volume of a point. So for a long time this was kind of a puzzle. Why do we have a finite omega 0? And then quantum mechanics kind of gave us an answer. Now let's determine what this omega 0 is for some systems that we had already discussed. For the ideal gas. Now, omega would be nothing but, in our case, the integral of dp dq, my volume element, over omega. Well, if my system, of course these are all 3n dimensional integrals. Well, Q is not bound, Q is restricted to some volume, some physical volume, V. So this should be V times the 3n P, such that E, the energy of my system, should be between some E0 plus delta over 2 and E0 minus delta over 2. This is the volume. If my system has energy E0, let's say, this is the phase space of the volume of phase space available to my system. And this is equal to V times the 3n dimensional solid angle times the p to the power 3n minus 1. So omega is V times the 3-dimensional volume element multiplied by p to the power 3n divided by 3n, where p goes from some minimum value to some maximum value. Now these minimum and maximum values of p are determined by the conditions on my energy. You see, the energy of my system was sum over pi squared over 2m summed over all particles. But this is p squared over 2m. This p squared over here that I'm writing is the 3n dimensional length of momentum. So the omega is actually V times this 3n dimensional solid angle times 2me to the power 3n over 2 divided by 3n, e from E0 minus delta over 2 to E0 plus delta over 2. So omega in this case is V. Well, this 3-dimensional solid angle, we had already calculated it last week, so this was our expression. Times 1 over 3n. Well, this is, let me write 2m to the power 3n over 2 times e to the power 3n over 2 minus 1. I'm taking the derivative with respect to e 3n over 2 times delta. I'm assuming delta is small compared to the total energy. So this is the volume available to my particles in phase space. Let me make the simplification. This 3n over 2 cancels this one and this one. So I'm left with V times pi to the power 3n over 2 divided by gamma 3n over 2 times 2me to the power 3n over 2 divided by e times delta. So omega for this system should be equal to v times delta over e omega 0. I'll just divide omega by omega 0. Now we had already calculated this omega. Let me, while the projector is turning on, let me just copy our previous expression. Okay, so I have just copied this omega qm from last week. Now there is one mistake I had made. You see, when I'm integrating over q, each one of these particles is constrained within a volume v, but there are n of them. So from each the integrals of the coordinates of each one, I get a factor v. So here I have v to the n. So here I have v to the n. Now these two expressions should be equal. Now let me just rewrite the previous expression that we had obtained in a way that looks similar to what we had obtained for the volume. This is equal to, well, there is a delta already. Let me divide by e. This is pi to the over 3n over 2 divided by gamma 3n over 2 times 2me to the power 3n over 2. Now if you just compare this line with my last line, well, the powers of e match. Here I have e to the power 3n over 2 minus 1. So the powers match. Here I have, let me also write the v times n. The powers of v also match. 2m is 2m to the 3n over 2, they match. The factors of pi do not match. Here I have pi to the power 3n over 2. Here I have pi to the power minus 3n over 2. So I have to divide by pi to the power 3n. Well, there is this additional 2 to the power n. Probably we have a mistake over there. That should be also 3n. This 3 probably we had missed it last week. And then we have, here we have an h bar to the power 3n. So here it should be h bar to the power 3n. 1 over. Now if I compare our expression for omega that we obtained today and omega that we obtained last week, you see, in this expression I have 1 over omega 0. So 1 over omega 0 should be equal to 1 over 2 pi h bar to the power 3n. Or 1 over h to the power 3, and this is what omega 0 is. For the free ideal gas, at least. Now, why do we have this H? Well, one way to understand this, at least qualitatively, is to look at the uncertainty principle. Which states that the uncertainty in the momentum of a particle multiplied by the uncertainty in the position of my particle should be at least of the order of h. H bar over 2 larger than or equal to h bar over 2, but which is of the order of h. Well, what this tells us is that, I mean, if you have a state, a quantum particle, you cannot really localize its state in phase space to a point. So it should have some width in delta p and the width in delta x. Kind of, to each particle, to each state, let's say, of a given particle, there doesn't correspond a point but a volume in phase space because of this uncertainty principle. And that volume is of the order of h. Well, this argument doesn't really tell us what should be the exact number, but it should be proportional to h. And if you have, let's say, for each particle, if you have 3 coordinates, well, then in each dimension, the volume is h, so just multiply this h cubed. If you have n of them, then you get n factors of h cubed, which is h to the power 3n. Again, I repeat, this argument doesn't really tell us what is the exact proportionality constant, but that we should just calculate studying systems both classically and quantum mechanically and comparing like we did here. And that number turns out to be always 2 pi h bar for each degree of freedom, for each dimension. Questions?
Can we find the same result by using the Planck length or something?
Planck length. Well, Planck length never entered into any part of this derivation. Planck length is something related with gravity. If you can treat a system taking into account the gravitational effects and treating it quantum mechanically, then you might get some corrections to this one. But since the systems we will be dealing with, at least in statistics, will be mainly just not gravitating objects, let's say, unless you are doing some thermodynamics of gravity or black holes, well, there wouldn't be any corrections. Okay, let's give a 10-minute break here. Then we will do, well, at least we can study one more system in which that fact omega 0 is exactly this one.